You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Role-based access control, or RBAC, and attribute-based access control, or ABAC, remain the two most widely used models in enterprises today. RBAC is attractive because it mirrors organizational structure, grouping permissions by job function. This makes it easier to scale and maintain, particularly in environments where duties are well defined. ABAC, on the other hand, adds flexibility by considering attributes such as department, device health, or time of day. Large enterprises often use both together, RBAC for broad assignment of permissions and ABAC for fine-tuned adjustments. This hybrid adoption pattern allows organizations to combine simplicity with precision, striking a balance between ease of management and security rigor. The strengths of RBAC include its intuitive alignment with real-world job functions and its simplicity of assignment. A new employee only needs to be placed in the correct role, and their permissions are automatically applied. A BAC's strength lies in its ability to adapt dynamically. Access can be granted or denied in real time based on conditions such as whether a laptop has the latest security patch. Enterprises with stable job structures lean heavily on RBAC, while those with diverse or dynamic environments lean more on ABAC. By combining them, organizations can cover both needs effectively. This recap shows why modern systems rarely depend on just one model. RBAC and ABAC complement each other, with RBAC handling the predictable and ABAC handling the contextual. For learners, it is important to see that neither model is perfect on its own, but together they provide both a strong baseline and adaptive flexibility. To make ABAC work, organizations need a way to describe policies clearly. This is where policy authoring languages and standards come into play. One example is the Extensible Access Control Markup Language, or XACML. Conceptually, XACML provides a way to write down rules in a consistent, machine-readable way. For example, a rule might state that only users in the finance department can access payroll records, and only if they are connecting from a compliant device. Policy as code approaches follow a similar idea, but instead of XML, they use programming-like syntax to define rules. These standards are important because they reduce confusion and enforce consistency. Without them, every system might describe policies differently, leading to errors. A policy language ensures rules can be shared, reused, and enforced across many systems. Beginners can think of them like grammar for access control. Just as grammar allows different writers to create sentences that everyone can understand, policy languages allow different systems to interpret and enforce rules correctly. The benefit of policy as code is that it brings access control into the same development processes as software. Rules can be versioned, tested, and deployed just like code. This makes them easier to maintain and less prone to human error. As enterprises scale, policy languages become essential for keeping order in increasingly complex environments. Attributes that feed ABAC decisions come from many sources. Identity directories, such as Active Directory or cloud-based identity services, provide information about the user, like department or job title. Device posture systems report whether a device has the latest patches, encryption enabled, or antivirus running. Business systems can also supply attributes, such as whether an employee is active, on leave, or assigned to a specific project. Each attribute contributes a piece of the puzzle that helps the policy decision point, or PDP, decide whether to grant access. The reliability of attribute sources is critical. If the HR system has not been updated to reflect that an employee left the company, the access control system may still treat them as active. Similarly, if the device posture system fails to report an update, a vulnerable device might be mistakenly granted access. This shows why attribute synchronization and data accuracy are just as important as the access control logic itself. Garbage in leads to garbage out, even in security. For learners, it helps to picture attributes like pieces of identification. A driver's license proves age, a badge shows employment, and a boarding pass shows flight eligibility. If any of those are inaccurate or forged, the decision made at the gate will be wrong. In cybersecurity, attribute sources serve the same role, and their trustworthiness is non-negotiable. Decision latency is another important factor. Every time a system asks a PDP whether to allow access, it takes time. If the PDP takes too long to respond, the user experiences delays or failures. In high-performance environments, even small delays can add up. For example, an online banking system cannot afford noticeable pauses every time a customer tries to check their balance. Access control must be secure, but it must also be fast. To address latency, caching strategies are often used. Instead of asking the PDP every single time, the system may cache recent decisions for a short period. Similarly, attributes may be cached so that they do not have to be retrieved from the source repeatedly. The challenge is to balance speed with accuracy. If caches are too long-lived, stale data might be used, leading to incorrect decisions. If they are too short, performance suffers. Caching can be compared to remembering recent answers on a test. If you just calculated the answer to a question, it makes sense to reuse it for the next similar question, rather than starting over. But if the question changes significantly, relying on the old answer can be dangerous. In the same way, caching must be carefully tuned to reuse correct information without extending its life past the point of trustworthiness. Audit trails provide the record-keeping backbone of access control systems. Every access decision should be logged, along with the attributes used and the final outcome. This creates a trail that investigators can follow in case of an incident. For example, if a sensitive file is accessed, the audit log should show who requested it, what rules were applied, and whether the request was allowed or denied. These records also support compliance. Many regulations require organizations to demonstrate not only that they have controls in place, but that those controls are being actively enforced. Audit trails provide that evidence. They also help identify patterns of misuse, such as repeated denied attempts that might indicate an insider probing for weaknesses. Think of audit trails like a security camera for access control. They may not stop the action themselves, but they provide visibility into what happened, when, and why. Without them, organizations are effectively blind after the fact, unable to prove compliance or learn from incidents. Delegation and hierarchical role models help organizations manage complexity. Delegation allows temporary or limited assignments, such as granting a user higher access while covering for a colleague. Hierarchical roles allow one role to inherit permissions from another, reflecting real organizational structures. For example, a manager role might include all the permissions of a staff role, plus additional ones. This avoids duplicating permissions across multiple roles and simplifies maintenance. These models also reduce administrative overhead. Instead of creating unique roles for every small variation, inheritance and delegation allow reuse and flexibility. However, they must be carefully monitored to avoid privilege creep, where users end up with more access than they should over time. Automated expiration of delegated roles and regular reviews of hierarchies help prevent this. For learners, delegation and hierarchies can be pictured like substitute teachers. A substitute may temporarily step into a teacher's role, but the assignment is temporary and should not continue once the regular teacher returns. Similarly, hierarchical roles are like layers in a company. A manager has both their own duties and the permissions of their staff. These structures reflect real-world organization and make access easier to manage. Risk-based access combines static policies with runtime signals to make smarter decisions. For example, a static rule might say, finance staff can access payroll data, but a runtime signal might add, only if they are logging in from the corporate network, not from an unfamiliar country. By combining the two, the system adapts to context. This approach increases security without creating unnecessary barriers for normal behavior. Runtime signals may include unusual login patterns, device compliance checks, or user behavior analytics. If risk appears low, access may be granted seamlessly. If risk appears high, the system may require additional authentication or deny access entirely. This dynamic approach is essential in modern environments where threats change quickly and static rules alone are insufficient. Integration patterns bring these concepts into real systems. Policy enforcement can happen at many levels, through API gateways controlling access to services, service meshes enforcing security within cloud-native applications, or operating system-level policies applied directly to files and processes. Each enforcement point has strengths depending on the environment. API gateways centralize control for external connections, service meshes secure internal communications, and operating systems enforce rules close to the resources themselves. Verification approaches ensure new policies are rolled out safely. Simulation allows administrators to test how a policy would behave without actually enforcing it. Canary enforcement applies a policy to a small subset of users or systems first, monitoring for problems before expanding. Staged rollouts gradually apply the policy to larger groups. These strategies reduce the risk of accidental lockouts or disruptions when new access rules are introduced. Remediation workflows address the reality that policies are not always perfect. Sometimes a rule may accidentally deny legitimate access or grant too much. Workflows must exist to quickly identify the problem, correct the policy, and reapply it. Without remediation, users may bypass controls out of frustration, weakening security. With clear processes, mistakes become opportunities to refine the system without undermining trust. A practical exercise brings these ideas together. Imagine designing an ABAC policy for financial records. The rule could state, deny access unless the user's department equals finance, and the device is compliant with security requirements. Testing this against sample users and devices allows administrators to confirm that finance staff on secure devices gain access, while others are denied. This simple example demonstrates how attributes, policies, and enforcement work in practice, reinforcing the core principles of ABAC in a hands-on way. Centralized and Distributed Policy Decision Point, or PDP, architectures each have advantages and drawbacks. A centralized PDP means all access requests are evaluated in one place. This makes management easier since policies only need to be updated in one location, but it may create bottlenecks or single points of failure. A distributed PDP spreads the decision-making across multiple systems. This reduces latency and improves resilience, but it can make it harder to maintain consistent policy enforcement. Organizations often use a hybrid approach, centralizing the definition of policies while distributing the enforcement to reduce delays. For learners, a useful analogy is a court system. A centralized PDP is like a Supreme Court making all decisions. A distributed PDP is like local courts handling cases according to the same rules. Both can work, but the trade-offs involve speed, consistency, and resilience. The choice depends on scale, performance needs, and tolerance for risk. In practice, global companies often use distributed PDPs to serve users across different regions. This avoids long communication delays while still syncing policies back to a central authority. The goal is to combine consistency with speed, ensuring users do not experience slowdowns while still enforcing the same rules worldwide. Multi-tenancy introduces another layer of complexity. In shared platforms, multiple organizations or tenants may use the same underlying system. Each tenant must have policies and roles that are isolated from the others. For example, a hospital and a university might both use the same cloud service, but their access rules must never overlap. This requires strong separation of data and policies so that one tenant's decisions cannot influence another's. Multi-tenancy also raises governance challenges. Each tenant may want different levels of control over policies, and the provider must balance flexibility with safety. The wrong configuration could expose one tenant's data to another, creating a serious breach. Designing access control for multi-tenant systems therefore requires extra rigor, isolation, and continuous monitoring. For a beginner, this is like apartment living. Everyone shares the same building, but each apartment has its own lock-in rules. The building's management enforces safety for the whole property, but tenants still expect privacy inside their own units. Multi-tenancy in digital systems follows the same principle. Policy governance is critical for maintaining access models over time. Governance means deciding how policies are created, approved, versioned, and retired. Without governance, policies may pile up in inconsistent ways, leading to confusion and errors. Versioning ensures that administrators know exactly which version of a policy is in effect. Approval workflows ensure that changes are reviewed before being applied, preventing mistakes from spreading. Regular review cycles allow organizations to prune outdated policies and refine existing ones. Think of governance like managing laws in a country. Laws are not written and forgotten. They are debated, approved, published, and occasionally repealed. The same is true for access control policies. Strong governance creates order, while weak governance creates chaos. Organizations that neglect governance often end up with conflicting policies that administrators cannot easily resolve. By formalizing how policies are created and maintained, they ensure the system stays consistent and reliable, even as it grows in complexity. Conflicts happen when multiple policies apply to the same request but give different answers. Conflict resolution strategies are necessary to handle these cases. Some systems use priority rules, where one policy overrides another based on rank. Others use combining algorithms, such as deny overrides or permit overrides. For example, deny overrides means that if any policy denies access, the request is denied regardless of other policies. This approach prioritizes safety over convenience. Conflict resolution ensures that the system behaves predictably. Without it, administrators might not understand why a request was allowed or denied, which undermines trust. By documenting and applying clear strategies, organizations can prevent confusion and maintain confidence in their access control systems. Learners can compare this to referees in a sports game. If two rules conflict, the referee needs a way to decide which one applies, otherwise, the game becomes unmanageable. Conflict resolution in access control provides that clarity, ensuring the game of access decisions remains fair and consistent. Policy observability is about monitoring and understanding how policies behave in real time. Dashboards can show decision latencies, meaning how long it takes to evaluate a request, as well as hit rates, meaning how often certain policies are triggered. Observability tools may also track overridden rules, showing where administrators had to bypass policies to keep operations running. This visibility helps organizations tune their systems, spotting both technical inefficiencies and overly strict rules. Observability is not just about performance, it also improves security. If administrators see that certain policies are constantly overridden, it may signal that those policies are unrealistic or poorly designed. On the other hand, if latency suddenly increases, it may indicate a problem in the infrastructure. Observability transforms policy enforcement from a black box into a transparent, manageable system. Privacy concerns also play a role in access control. Many attributes used in ABAC involve personal data, such as location, department, or device information. Regulations like the General Data Protection Regulation, or GDPR, set strict rules on how personal data can be collected, stored, and used. Organizations must ensure that attributes are only used for legitimate purposes, stored securely, and minimized to what is necessary. Collecting more data than needed not only violates privacy but also increases risk. Machine-assigned risk signals are becoming increasingly common. Systems can automatically generate risk scores based on behavior patterns, such as detecting if a user logs in from a new country or at an unusual time. These signals can then adjust policies dynamically. For example, a low-risk login might pass normally, but a high-risk login might trigger multi-factor authentication or even be denied outright. This adds a real-time, adaptive layer to access control. Fallback behaviors are essential in case the policy service is unavailable. If the PDP cannot respond, should access be denied by default or allowed? Safe defaults usually mean denying access, but this can cause business disruptions. Allowing access, however, could create security gaps. Organizations must carefully decide and document fallback rules, balancing availability with protection. This ensures systems remain predictable during outages. Testing frameworks are another important piece. Policies should be tested the same way software is tested, using unit tests, synthetic requests, and full end-to-end validation. Unit tests check individual rules in isolation. Synthetic requests simulate real-world access attempts. End-to-end validation ensures the entire chain of decision-making works correctly. Without testing frameworks, organizations risk deploying broken or incomplete policies that disrupt operations. The value of mature access control can also be measured in business outcomes. Useful metrics include fewer help desk tickets about access problems, lower rates of privilege creep, and faster onboarding times for new employees. By tracking these outcomes, organizations can demonstrate that access control is not just a security tool, but also an enabler of efficiency and productivity. Finally, organizations must decide between vendor-provided PDP solutions and building their own in-house. Vendors often offer faster deployment and proven interoperability through standardized APIs, but may limit customization. In-house solutions allow greater flexibility but require more resources to maintain. Many enterprises use vendor tools for core functions and customize at the edges. The key is interoperability, ensuring that policies can integrate smoothly across systems. In the end, mature access control combines clear models, automated enforcement, and continuous validation. It is not about choosing one perfect model, but about building a framework that adapts to organizational needs, balances security with usability, and provides transparency through audits and monitoring. With strong access control in place, organizations can confidently manage who gets access to what, while maintaining trust and accountability at every step. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.